Hi, I'm Beth Dickey of the NASA Office of Communications. Welcome to The Leading Edge, an aeronautics show where we take an in-depth look at aeronautics problems that NASA is working to solve through its own research or in collaboration with others. Today's topic is data mining and how it can be used to improve aviation safety. Modern airplanes produce volumes and volumes of data, and NASA is working on ways to use that information to find problems before they lead to accidents. To begin to understand what data mining is and how it can benefit the transportation system, we spoke with two of America's experts on the subject. Jaiwei Han has co-authored or co-edited several books, 350 papers, and organized more than 100 conferences on the subject of data mining. Stephen Boyd specializes in mathematical optimization of huge data sets. He's been a visiting professor at 9 prestigious universities around the world and holds an honorary doctorate from the Royal Institute of Technology in Sweden. Both men have more than 20,000 citations to their credit. Here's what they had to say.
Data mining is the art of digging through mountains of information to find something useful when you're really not sure what you're looking for.
It is an exploration, it's a discovery process. That's why data mining, some people call it knowledge discovery from data.
Jaiwei Han literally wrote the book on data mining concepts and techniques. His textbook by that name is used by college students around the world.
There's so much data. People want to dig in, want to find patterns, want to find outliers, want to find the rules, regularities. This is very valuable because we are living in a data explosion age. Some people say we are submerged or soaked with data, but we still lack knowledge. Okay, so if we want to really getting knowledge to discover things useful, we have to make use of the data.
We all use data mining every day.
One example would be fraud detection for credit cards. They're constantly monitoring transactions to see if they're typical, atypical, or might indicate fraud. Another, of course, is recommendation engines. You go to Netflix, you go to Amazon, and you'll get sometimes laughable, but often by a computer, of course. You will analyze this data, and you'd want to tease out little patterns and things like that. Of course, you have to be careful that you're not just picking up stuff that was just a fluke in the data, so you want to be sure that what you're picking up is real.
NASA is studying how data mining techniques can be used to improve aviation safety. Collaborating with commercial carriers like Southwest Airlines, NASA aeronautics researchers are developing complex algorithms or computer programs that can help safety analysts find precursors or early indicators of safety concerns. In tests using data from actual completed flights, the algorithms have detected potential problems that might otherwise have been overlooked. Commercial airliners typically log data from hundreds of instruments at least once every second. The flight data recorder stores numeric or symbolic readings on everything from altitude and airspeed to the positions of flight controls, such as wing flaps and landing gear, to the settings of switches for the electrical and hydraulic systems when the airplane is in the air. Back on the ground, pilots supplement the airborne data with written reports about the flight. Taken together, all this data tells the story of what the airplane was doing. But there's so much data, it's been nearly impossible for airlines to do anything other than look back for the cause of something that's already happened. The Aviation Safety Challenge is to figure out how to use the data to look ahead and find precursors to problems. We need to be able to sort through the data to see if there's anything unusual, and then zoom in on those bits of information that are different to better understand them. And we need to do it quickly and efficiently.
You may want to get something unknown, you want to predict something. We call predictive modeling. The knowledge discovery, the magic or the attractive things actually is you work out your hypothesis or discover something and try to find something unknown, predict something.
What this will do is it will look at lots of data where things are just off a little bit. A human being wouldn't even notice these differences. But you start integrating this across like 2 or 3 flights, and something's out of whack. These are the kind of errors that things like this can catch. And these could actually end up having very valuable safety implications, right? You could catch things like impending failure.
Data mining is a lot like detective work. You dig for clues, and what they uncover will help make your next flight.
Is collaborating with NASA to use data mining to improve its flight safety and its efficiency. Let's talk a little bit about how airlines do use data mining and why they do it.
Well, it's a very complex system, Beth, and probably the most complex system that humans have ever built. If you look at the Bureau of Transportation Statistics website, you can see that the top 20 carriers fly about 750,000 flights per month, and Southwest alone flies about 100,000 flights a month. So we have a lot of data, and we're using that to improve our safety, customer service, and efficiency.
Now, I think we have a depiction of a typical day in the life of the nation's air transportation system. Coming up on the screen in just a minute, you're going to see a map of the United States with the whole yellow is going to move across to the West Coast during the day. That's an awful lot of airplanes. It just must be impossible to keep track of all the problems that could occur.
Well, it is very complex, and at the same time, it's safer than it's ever been. And that's why our partnership with NASA is very important, because we need to have systematic ways to look into our data and find things that we're not currently looking for and put mitigations in place so that we do improve safety.
Well, what kinds of problems do you find right now?
We see a whole range of problems, from pilot reports of specific problems at airports, to issues in the data, whether it's mechanical problems with aircraft or even specific arrival and approach abnormalities.
We don't see airplane crashes every day, so obviously something's going right. What are the consequences of these problems?
Well, often there are no consequences, and that's one of the things that we want to continue. We're doing everything we can do to make the system as safe as possible. Back in 1931, Dr. Heinrich developed this model to describe or to sort of look at safety in complex systems, and I don't think he anticipated the complexity of the modern aviation system, but what it does tell us is that there are a lot of issues down at the base of the pyramid that we can take advantage of. We can analyze that data to try to prevent things occurring farther up the pyramid.
All right, so let's talk about the data you collect.
Okay. Well, we have 3 main safety programs. We have an Aviation Safety Action Partnership Program, we have a Flight Data Analysis Program, and a traditional Flight Safety Investigations Program.
And do these all work in conjunction with each other?
Well, they do. We have agreements between our pilot association and the FAA and the company on how we govern those programs. And we do gain some benefit from seeing something in one program and then analyzing the data in other programs to find out more about a specific event.
All right, well, let's look at them individually. Talk about the ASAP first.
Okay. ASAP is an agreement between the company and the Pilot Association at Southwest and the FAA, where pilots can report voluntarily safety issues that they experience while they're out flying. The FAA has made it possible and provided incentive for the pilots to report, because if the pilot submits a report and meets requirements for entering the program, then they receive protection. So the FAA has agreed to limit whatever certificate action may occur if there was a violation of a regulation. Now, the benefit is we have a safe, non-punitive environment for pilots to report, and the company receives the benefit because we have a lot of information about events that we would otherwise not know about, and we're able to take that and make systemic corrections to improve our safety.
All right, and what about, you call it FADAP, the Federal Aviation Administration calls it FOQA.
Right, Flight Operational Quality Assurance, or Flight Data Analysis Program. We have to be just a little bit different, because that's exactly what we do. We download data off of the aircraft every 5 to 7 days from a memory card. We put that into our database, and our analysts go through the data and they determine what exactly is going on with the airplane. And that's the benefit of FDAP is we analyze about 50,000 flights a month, so about half of our schedule we look at, and we're able to tell pretty much what's going on with our aircraft.
And what was the third program?
That was Flight Safety Investigations Program, and it's a very strong program. It's a forensic type program, a traditional flight safety investigation program. And if you think about that model, the pyramid, the FDAP and ASAP programs are looking at data that we get from the bottom of that pyramid, trying to prevent things farther up the pyramid. But obviously, we have a strong investigations program when we do need to take a look at that.
What's the ultimate goal that you have in collecting this information and assessing it?
Well, ultimately, we're looking at improving safety through risk management. So we want to identify hazards in the operation. We want to analyze the risk that they present and then put mitigations in place to control that risk and improve our safety and efficiency as well.
All right. Now, NASA administers something called the Aviation Safety Reporting System for the FAA. How does all of how do all of the programs that you've told us about fit into that?
Well, ASAP, the Pilot Voluntary Disclosure Program, really grew out of ASRS. And ASRS is a program where any aviation professional in the country can submit a safety report. And they are analyzed at NASA, and the database is made available for other people to take a look at as well. And virtually all of the airlines that have ASAP programs participate by submitting ASAP reports into the ASRS database.
And Southwest does that?
Yes.
And what do you get back? Any benefit?
We do. In addition to the safety alerts that are produced by the analysts at ASRS, when we initiate service into a new city, we work with NASA to come up with a set of disclosure or a set of reports that pilots have submitted that may indicate issues that our pilots need to be aware of before they have an opportunity to fly there. So we put together what we call a SMART pack that's a synopsis of the events that were reported by other pilots and aviation professionals. So it's got airfield diagrams and charts and some overhead imagery so that we can provide our pilot with a first look that provides them an opportunity for success.
So
it's based on looking at exceedances, and it is a forensic type approach. Our ASAP program is the same type of thing where pilots are reporting things that they observe out in the operation.
how would a predictive insight that you could gain from data mining help you in those kinds of situations?
Well, we're looking at ways to find events and issues that we're not currently aware of or we're not currently looking for, and that's why the partnership with NASA is so important. We want to be able to find out what the hazards are, measure the risk, and then put those mitigations in place.
Have you ever been able to detect a problem, an anomaly, before a pilot has?
Well,
and what happened?
NASA has done some very interesting work on fuel burn, and by taking a look at nominal fuel burns between city pairs and then analyzing what happens in different environmental conditions, we can gain some efficiency out of that. But going further into that information, we can even compare the performance of each engine on the same aircraft and detect small divergences in parameters that may lead to another problem. So that's kind of what we're hoping for in our partnership with NASA, is to be able to take a forward-looking approach and find small things that pilots may not necessarily detect and fix them before they become a service interruption.
All right. And what else do you think you can glean from the collaboration with the agency?
Well, we've got that partnership that we.
I'm guessing that it's a systematic kind of.
Oh, well, yes. We want to develop a systematic approach to our data because we have so much data. We want to be able to take a look and find out those issues that we currently weren't looking for because we really don't want to miss anything in the data.
And this kind of thing can help you prevent delays and cancellations, can't it?
That's true. There's, as we get safer, we have to go farther and farther up the stream of data, and what we find is that there are efficiency benefits and customer service benefits as well.
All right, great. Now, the open source website NASA has called DashLink. This is a place where people can go and download software for data mining applications and whatnot. Has Southwest taken advantage of that?
Yes, we've worked with the analysts from NASA and taken advantage of a couple of those algorithms, and the things that we have learned from analyzing sets of data involving over 7,000 flights have been incorporated in our daily review of flight data.
All right. I'm curious if you can tell me a story about data mining saving the day.
Well, my first experience where I really got excited about data mining was when we first started looking at high energy approaches in our flight data, the FDAP program. And we saw a number of instances where we had high energy approaches at certain airports, but in our ASAP pilot reporting data, we really didn't see a lot of pilots talking about that. So we got an application from NASA that was developed by Dr. Michael McGreevy called Paralog, and we were able to take a very good report from a pilot about a high energy approach and search for other examples of that same situation. And what we found was very interesting because we discovered that there were airspeed and altitude requirements on arrival that were creating a very busy environment in the cockpit, and pilots often just forgot to switch the radio and talk to tower, so they were reporting it as a communication issue. But we were able to take that information and go back to air traffic control and work with them to modify the way they bring us into airports to provide a better arrival.
So that's a good example of how you're sort of shifting from that forensic approach to the prognostic kind of approach.
That's right,
and
making
the predictive analysis.
Systemic corrections and helping things in the future become more safe.
All right. How would you use data mining to, let's say, monitor the health of an airplane?
Well, we can take advantage of the redundancy of the system. So, for instance, we have systems that are supposed to perform in a very similar manner. We can look for small differences in the way those systems are performing in the individual parameters, and then we can possibly determine there's an issue before the pilot becomes aware of the problem and alert maintenance so that they can correct it before it becomes interruption.
I think you had told me earlier about an example of using this kind of information to work on engine cooling operations.
That's true. Well, and fuel is very expensive, so as we were looking at ways that we may be able to save a little fuel on the taxi-in after landing, we also need to take into consideration engine cooling. And there's a requirement to cool the engines for 1 to 3 minutes after you land. And once that condition is satisfied, then we can turn off one engine to save a little bit of fuel as we taxi in. And because it is important to get that adequate cooling, because the long-term impact of taking good care of the engines is increased engine life. Because over time, if the engine is not allowed to cool properly, the oil jets that feed lubrication to the bearings can become clogged. So we want to be very careful about that and improve the long-term health of the engines. But at the same time, if we can take advantage of some fuel efficiency, then that's great as well.
Do you fly?
Yes.
How has data mining helped you?
Well, that specific example of engine cooling has really allowed me to go in and develop different strategies on how I monitor the engines after I land, so that I can take better care of the engines and get a little fuel efficiency. But beyond that, our analysts have done some really good work on arrival paths at specific airports. Specifically, El Paso is an example because of the high terrain to the west, and requires a higher altitude on arrival. And our analysts did some interesting analysis where they laid down tracks to show the difference between an optimum profile and maybe one that's a little too tight. And so that has really influenced the way I approach that airport and provides a better, more comfortable ride for the customers, as well as an optimum path.
All right, well, great. Jeff, thanks for coming along and giving us a little bit of insight into Southwest's air safety operations. We're so glad you could join us. It's interesting to see how NASA's data mining expertise is being applied in industry. In a moment, we'll take a closer look at the work NASA's doing to do research in data mining for aviation safety. But first, we want to give you an opportunity to get acquainted with one of our 4 aeronautics research centers, the Dryden Flight Research Center in California. watching the Leading Edge, an aeronautics research discussion program brought to you by NASA. Our topic today is data mining and how NASA research is helping to make air safety better. Leading this section of our discussion is NASA's Associate Administrator for Aeronautics Research, Jaewon Shin, and he'll be speaking with Ashok Srivastava, who is the project manager for, this is a long title, so correct me if I get it wrong, System-Wide Safety and Assurance Technologies in NASA's Aviation Safety Program. Dr. Srivastava is also the leader of the Intelligent Data Understanding Group at NASA's Ames Research Center. His group performs data mining research in a number of areas in aviation safety and application domains such as earth science to study global climate processes and astrophysics to help characterize the large-scale structure of the universe. He's the author of many research papers and on data mining, machine learning, and text mining, and currently editing 2 books. Man, when do you find time to work? On data mining applications in astronomy and health management. Dr. Shin.
Thank you, Beth. Ashok, it's good to see you again, and thank you for being here with us. We just heard from Captain Jeff Hamlett about the progress Southwest Airlines making using NASA's technologies to address their maintenance, and not only maintenance, but efficiency interest. You're here to talk about NASA's interest in data mining. So why don't we start talking about data mining in general terms?
Well, thank you, Jaewon, and thank you for inviting me to speak here. It's really a pleasure to be here. NASA, as you know, has some of the largest and most complex data sets in the world. To give you an idea, for instance, in the Earth sciences, we have satellites orbiting the Earth constantly, taking measurements at very high resolution, sometimes 250 meter square resolution across the whole globe. And all of this data is streaming in to our systems, and it needs to be analyzed and understood. If you look at space systems, for instance, we have telescopes looking out into space, taking data at an unprecedented rate. Sometimes people say in tens of terabytes or even petabytes of data is accumulating from some of these systems. If you look within the Earth's atmosphere at aeronautical applications, we just heard from Jeff saying that there are major carriers accumulating 100,000 flights per month. Within the United States, there's about 10 million flights per year. All of this data that's accumulating needs to be analyzed and understood to improve quality of life for the public. And what we're doing is developing tools and techniques so that people, for example, in the safety industry, can take these algorithms, take these computer methods, apply it to data, and understand something useful that could have some good benefit from the safety perspective.
Great. It is mind-boggling to think about that amount of data. So what particular technology are we developing, and what is its relevance to flying public?
Well, one of the key issues that comes up in the area of aviation safety and trying to understand some of these issues is that we have small events that are occurring, for example, in the national airspace. And these small events, when taken together, can form a bigger picture of some key issues that are occurring. And we need to develop algorithms that can actually sort through and understand that so that an analyst can really make use of it and make good decisions. One of the key issues that we face is that these anomalies can really start to creep up, and as they creep up, they can lead to bigger problems in the future.
So what sort of information are we talking about here, and how much of it is out there?
Well, again, if you go back to this example, we have about 10 million flights occurring within the United States. Each airplane might be outfitted to obtain maybe a few hundred parameters of data. Each parameter is sampled once per second. So this is an astronomical amount of information. On top of that, we have text reports. And these text reports are written by pilots, they're written by co-pilots or other members of the flight crew. We're trying to take all of this information together in order to discover an anomaly. Sometimes this is like looking for a needle in a haystack, which means that we're really trying to figure out if there's something small that's occurring that could lead to a bigger problem. I think we have a slide on the idea that in the past we were looking at forensic information, and I think that's very important. We should continue to do this, where you basically look for the last accident. What happened, why it happened, figure all of that out, and then try and make sure that doesn't occur again. What we're moving to, though, is a more prognostic approach. And in the prognostic approach, it's really about looking at the data and what it's saying at this moment, and then making a prediction into the future and saying, 10 minutes from now, 10 hours from now, 10 days from now, something bad could happen. And so we need to make the right decision. So we're moving from forensics to prognostics, which is, I think, an important development in the industry.
Ashok, your needle and haystack analogy is very intriguing. Can you tell us more about that?
Sure. When we're searching for something that's rare or something that is a precursor to a failure, one of the key issues is that we need to validate it and make sure that that thing that we're discovering isn't just another needle in the haystack, or another piece of hay, I should say, in the haystack, that it's really something different. And we're fortunate that Dr. Nikunj, who's a member of my group at NASA Ames Research Center, is an expert in the field of data mining and machine learning. And we're going to have a video now in which he discusses some of the applications of data mining in anomaly detection. So if we can roll that video.
I lead a team of 7 of us that look at data from commercial aviation and develop tools and technologies for data mining on that data so that analysts can use that to find operationally significant anomalies. If our algorithms identify something as being anomalous, that's not necessarily bad or necessarily dangerous, it's just unusual. But those are the candidates then that we would present to a domain expert and say that maybe ask if maybe some of those are operationally significant. We at least assume that that overwhelming majority of flights that are similar to one another are normal, and so there probably are not operationally significant or dangerous events occurring within those flights. I often like to give the example that is probably fairly popular is looking at, in case of supermarkets, you look at so-called market basket analysis. So you look at customers and what their buying patterns are, and you might then try to group them in different ways, and then basically act based on those groups rather than based on individuals. And in some way we do that here as well. So within aviation safety, like I was mentioning, we identified that large block of normal flights, but then we say, okay, here are some groups of abnormal flights, and then we try to learn something about those particular anomalies, try to determine, are they operationally significant or are they just statistically unusual. So essentially, we ask the question, what data is kind of most unusual relative to the rest? We definitely try to make our algorithms useful to analysts. So in fact, we have deployed some of our algorithms at FAA and at some airlines, and they have tested these algorithms and given us feedback on how well our algorithms are doing, and also how we can make them better, make them more efficient, help them find the events that they're interested in more quickly and in a more focused way.
So Ashok, Nikunj gave us good understanding of what needles we're looking for in the haystack, so to speak. But he mentioned showing the results to domain experts. Who are they, and what do they think about needles that we're finding?
Well, one of the most interesting aspects, in my opinion, of data mining is that we don't do it in a vacuum. We actually do it hand in hand with domain experts like Jeff or other people who are really interested and knowledgeable about the operations that we're trying to analyze. So in the next video, you're going to see 2 people who we work with closely. One is a gentleman named Brian Matthews. Brian is a member of my group, and his job is to develop and then validate the algorithms that we have on real data. And so he goes through and he sees the nature of the results that are coming up. But we also have a captain, a retired captain of a 777, who works with us for the last many years, and his name is Bob Lawrence. So Brian and Bob work together in order to look at the results that are coming off of the computer programs, the algorithms that we're developing, and then Bob can give us some insight into the operational significance, because what we want to do is really discover information that's useful for the flying public, useful for the carriers, useful for the FAA. And so this is the way we go through and use our domain experts. So the next video will show you Brian and Bob interacting and some of the results that they've gotten.
I'm retired airline captain Bob Lawrence. I flew for 33 years for a major U.S. airline, and subsequently for 8 years managed a NASA project called Aviation Performance Measuring Systems. And I'm currently working with NASA's data mining group as a domain expert to help relate their scientific results to the world of commercial aviation transport.
My name is Brian Matthews. I've been at NASA AIMS for about 9 years. I've recently started working in the Aviation Safety Program, where I've been tasked to find anomalous events in enormous amount of aviation data. I work with Bob, and once we find anomalies that we've detected with our algorithms, we use Bob's expertise to determine if these anomalies are operationally significant for the airlines.
Well, there are basically two kinds of data currently that we're working with: numeric data and text data. Text data, of course, is pilot reports, incident reports, flight safety reports. The numeric data comes from a flight data recorder, which is measuring things such as switch positions on the control panel, warning modes, the position of the flight instruments themselves, altimeters, airspeed, the positions of the flight controls, whether it's the aircraft yoke or the throttles or the landing gear or the flaps or the spoilers.
We can deal with up to millions of flights a year from some airlines.
It's such an interesting exercise when Brian and I sit down in front of a computer screen and look at the anomalies that the program has come up with. And then we try to explain what was going on. What's the story here? What story is being told? And so we'll select different parameters to look at, and we'll go through and try to explain what it is that was going on. And sometimes it turns out that what was happening was a completely normal thing. But then once in a while, we get one of those gems, which is very interesting to an airline analyst, and we hope that they will find our software useful in the future.
It's like playing detective, where you're not able to interview the airline pilot, but you have all this data that you can sift through and display different modes of the flight, and then the expertise who's been there can kind of determine what was actually happening during that flight.
From the point of view of a pilot, I am painfully aware of the fact that I have only personally been exposed to a small part of the operation myself. I find it very comforting to know that there are people out there who are constructing the big picture and then analyzing it to pick out what could possibly happen. Most of what could possibly happen has never happened to me personally, but it's happened. But when you add together all of the anomalous events and you construct a big picture out of that, then you can start to deconstruct it and fix it.
Great, Ashok. I would say that's really good teamwork right there. I think we're getting good education of what we are looking for and how it relates to real-life situations. But could you say more about the complexity of the task?
Sure. What we've noticed in the pursuit of data mining in the area of aviation safety is that we're trying to look for what we call precursors, or these are small events that could be occurring at different times. So something happens now and then something happens a little later at different places, different locations. And we're trying to pull all of this together in order to obtain a big picture of what's going on. I think Bob touched on it very nicely, that any one person gets only a sliver of information, a sliver of experience about what's going on in the national airspace. But what we're trying to do is understand it in all of its complexity. And that's a difficult task. That requires algorithms that can scale, which means analyze and process massive amounts of data. It requires algorithms that can process different kinds of information that's coming at different times. It also requires the ability to know when you're right and when you're not wrong, and also some measure of confidence. And so all of these things taken together, if you think about it, becomes very complex. But in my opinion, that's where the reward lies. That's what makes this such an exciting field, because we're really doing something that has a lot of impact potential, positive impact for the flying public. So it's very exciting.
Great. I think it's not going to be very difficult to imagine that this kind of technology can benefit not only air transportation system, but also space systems. And I understand you actually had such a case to help space shuttle program. Could you say more about that?
Sure. You know, a couple of years ago, I remember it was on Valentine's Day. It was a Saturday. My cell phone rang, and it was a colleague of mine from Kennedy Space Center who had called up to find out whether or not we could apply some data mining techniques to discover a potential anomaly on a shuttle mission. And so this was just before STS-119, and I think on the monitor you can see the launch of that particular mission. What we did is developed some algorithms that could be applied to the main propulsion system of the space shuttle and to detect anomalies in one of the hydrogen lines that was there. And it turns out that we were able to detect it, and that information went up into the Flight Readiness Review through the NASA Engineering and Safety Center to the Flight Readiness Review. And I think they used some of that information in making a determination about the next launch. So we were really pleased to see how data mining could, in short order, affect an important mission like STS-119.
That's wonderful. Ashok, in the case of STS-119, you received a request to look into something. But if you were going through commercial airline data and say you ran into something noteworthy, how can we inform about that data, and what can we do about it?
Well, if we see something in data using one of our algorithms, we notify the airline, and they then go and do further analysis, determine whether or not what we've discovered is useful, and then they might take some implementation, make some implementation based on that. But I think it's important to remember that NASA is developing tools and technologies so that others, like the FAA, like the carriers, other safety analysts, can really go through and analyze and manage some of that data. Another aspect of the issue is that we really don't have identified information. In other words, our data doesn't say the tail number of the aircraft, it doesn't identify pilots, or give really other identifying information. And so what happens is that we use the data to validate the algorithms, to check to make sure that they're doing something useful, but then we transition it over to carriers such as Southwest. We're delighted to be working with them because then they can take it, do further validation, and then operationalize it. They've already done that in the past, and I think that with our partnership we hope to do more of that in the future.
Great. I think folks would agree that this is a very exciting area to improve aviation safety, but we actually do quite more than just data mining, right, in aviation safety. Could you say more in broader terms what we're doing?
You know, data mining is really the tip of the iceberg when it comes to aviation safety. There's so much going on within NASA, within the aviation safety program. For example, there's significant research going on in the area of icing, understanding how icing affects both general aviation aircraft but also commercial aircraft. Understanding lightning and the effects that lightning can have on both types of aircraft, I think, is another important area of research. We have research going on in an area called vehicle health management, which is really looking at the detection and prediction of adverse events on a single aircraft. That's very important. We also have work going on in the human factors area, where we try to understand how humans and these complex machines and then sets and so many of these machines interact in a seamless fashion. So there's a lot of work going on in a number of areas in aviation safety, and data mining is one of those areas which is hopefully going to have an important impact in the future.
Good. Ashok, I feel very fortunate, and I think I'm speaking for everyone in NASA aeronautics community, to have you as one of our members to make this very, very important progress in technical development. But I'm curious, what led you to NASA?
Well, many years ago, I was contacted by the Chief of Information Technology at NASA Ames Research Center, and he said that if I came to NASA, I would be able to set the strategic direction for data mining within the agency. And since I was a child, I have to say that NASA and the problems that it has have really captured my imagination. They're amazing, fascinating problems, and to be a part of that, I think, was really something that I couldn't turn down. After coming here and then realizing that we could work in aviation safety and having a potential impact there for millions, if not billions of people around the world, I thought this was an amazing opportunity. You know, when I was a child, I used to go with my father to the airport because he used to travel a lot, and I would see these airplanes taking off, and it had left such an impression on me that I wanted to be part of that, and I'm really delighted to be here at NASA and part of the aviation safety program.
We're very, very delighted as well. Ashok, thank you very much for very exciting and enlightening education that you have given us today. And I think this is a great example with your lead in this work, and also Captain Hamlett's collaboration with NASA. Such a great example that we are working together to help flying public. So thank you for your leadership, and thank you so much for everything you're doing.
Thank you for the opportunity.
Next, we'll take some questions from our audience, but first we want to get you acquainted with another one of our aeronautics research centers, the Langley Research Center in Virginia.
Before flights, there are ideas. Before missions, answers. And before exploration comes innovation. It's the way NASA works. And for nearly 100 years, a first stop for answers and ideas, the Langley Research Center, the birthplace of NASA. This is where the aviation industry we rely on was created, where astronauts trained and the space program was launched, and where, right now, climate change is being tracked from space. Today, the Langley Research Center jumpstarts what's next for NASA and what makes life better for all of us. Here, the scientists, engineers, and creative problem solvers have innovation in their DNA and tackle some of the most complex challenges of our time, like designing greener, quieter aircraft and a safe interstate skyway, developing the earliest robotic spacecraft, and paving the way for planetary exploration, uncovering how our atmosphere is changing and how that impacts everything from air travel to climate change, and making renewable energy sources viable, not just vital. Langley's is a vision of safer, faster, more affordable airplanes, of personal journeys into space, of a world where climate change is no longer a threat. It's a vision based on answers and ideas. And with those, Langley is creating the future.
You're watching The Leading Edge, an aeronautics research discussion program brought to you by NASA. We've been discussing data mining today and NASA's work to improve, to enable the airlines to improve their aviation safety and the safety of your flight. Our panelists today are Jeff Hamlett of Southwest Airlines and Ashok Srivastava of NASA's Aviation Safety Program. Now's the opportunity for members of our audience to ask questions. We'll start with questions from those here at the headquarters auditorium and then from employees participating remotely around our centers. Anyone here in the audience with a question? Right here.
I have a question.
Please wait for the mic. Thank you.
I have a question. You've talked a lot about integrating information from text sources with quantitative data. Can you tell us more about how you do that? It seems like so many fields could use methods to integrate narrative data with quantitative data.
Sure. One way that we do this is we have developed a methodology or an approach, a mathematical approach, which treats all data as one, independent of where it comes from. So it could take text, it could take numbers, it could take other kinds of data structures like trees and graphs and networks, and it combines it all into a single mathematical framework, and then you turn a crank. And when you turn the crank, you get out a prediction algorithm, you can get out an anomaly detection algorithm, classification, and so forth. So that's the approach that we're taking currently. There are some top people in the field of machine learning and data mining from around the country that are exploring complementary approaches, but this is one of the approaches that we're taking right now, and we're hoping to see, in partnership with Southwest, some benefit coming out of this research.
Anyone else here in the auditorium? There's one over there.
Hello, my question is for Dr. Srivastava. You had mentioned in your explanation of analyzing the data that you are able to make some predictions about when airline or airplane parts may fail, such as maybe you've said in your example, 10 minutes, 10 hours, et cetera, et cetera. What is the range that you can predict in the future, from immediate future to, in maybe even years to come? And in that range, what is your percentage error? What is the accuracy or precision of your predictions?
Those are great questions. So in the case, it depends on the system and the subsystems that we're talking about on a particular aircraft. We're looking at, it's important to remember that we're looking at information from components of an aircraft all the way up to the national airspace. So because of that, it changes the range of our predictions and the way we measure accuracy. So for example, if you take a specific component of an aircraft, for example, an electromechanical actuator, some of our partners at NASA Ames Research Center are developing technologies that can pretty accurately predict when that actuator is going to fail. Now, it turns out actuators don't fail very often. Maybe I've heard after millions of hours of operation, there might be a failure. So these are extremely rare events. What we're looking at, though, in data mining is really the confluence of a number of different factors that could lead to a problem. So it might be that the component is a little off on an aircraft. It might be that the aircraft in front is having a little bit of a problem. It might be that the pilot has some fatigue. And taking all of these things into account, what is the likelihood of a problem? So measuring accuracy in that context in itself is difficult. So it's hard to say what our accuracy or precision or recall is in those terms. But that's something that we're actively researching.
All right, I've got a question for Jeff. I was intrigued by your discussion of the 3 data collection programs. Can you tell us a little bit more about how those programs interact or how they may or may not work together?
Sure. All those programs are, well, the ASAP and the FDAP programs are voluntary programs that are really formed on the basis of a very strong relationship with our pilot association. And one of the things that we really work hard to do is preserve the de-identification of events. So one of the things that we're not able to do is take a pilot disclosure from ASAP and then go into FDAP and look for a specific flight that may have had that same profile. But what we can do is take the concept of the event that occurred and develop an algorithm to go look for, and in an aggregate sense, look for those types of events that occur in the data. And both of those, it works both ways, where we can see something in FDAP. I think I talked about that earlier, and we can go search our database in ASAP to get the explanation of why that's occurring, and then we can know exactly what's happening with the aircraft through our FDAP program.
All right, and we do have some questions that have been submitted to us offline, and this is an interesting one, I guess for Ashok. Could you use Google to mine the data you get from airplanes, at least the written reports?
You know, it's a question that I get a lot regarding Google, because Google is ubiquitous. Everybody uses it, and people can reasonably say, can you use this to analyze text reports? And I think the short answer is yes. You could use it to look at the text reports and get some idea of what's in there. It's basically a search engine technology applied to text, which makes perfect sense. What we're doing is looking at not only the text, but also the numeric data coming off the aircraft. And so far as I know, that's not something that Google does at the moment, but you never know. They could get involved. We have had a partnership with Google for many years in some of these areas, and some of the technologies that we've developed in analyzing numeric data has been done in that partnership.
All right. Do we have any more questions here way up in the back?
I think this is a question for both guests. I get this vision when you're describing the process of Jodie Foster in the movie Contact, you know, sitting on the hood of the car with the headphones and just listening and listening and waiting forever and ever. So I was just curious, like, when you're looking for that needle in a haystack, what does it look like when you find it? And then what is the handoff like when you give that information? I know you said, Ashok, you make it available to all the airlines, but what does that transition or handoff or, hey, we found something look like from NASA to someone like Southwest?
So when we find an issue in the data, oftentimes it turns out to be perfectly known. Everybody in the industry knows about it, and we didn't. And that's actually a good thing, because that's kind of validating the algorithm. It's saying that it found something useful. And so we might talk to Bob, we might talk to Jeff, and get that kind of a response. Sometimes what we find, frankly, is useless. It's something that's just noise or a spurious result, and so Bob or Jeff tells us, usually in a nice way, that, hey, this isn't really useful. But sometimes we find something that's actually useful. And there was a nice example of this in working with Southwest a couple of years ago, where we found something. Actually, they found it using our algorithms, and then I think the transition was very smooth. They were able to take that and then operationalize it. Maybe Jeff can talk a little bit more about that process.
Well, and that's exactly right, because if we do find something, often it may be just a parameter validation issue. It could be just a problem with a sensor on the aircraft that's delivering bad information. But in this case, we were able to work with the algorithm that was written by NASA, and then take it and sort of customize it so that we could use it within our normal library of algorithms that we use for looking at data on a daily basis, and get some benefit. So it does take some transition and tailoring for our purposes.
One of the things I'm particularly excited about is that the work that we're doing is for the public's benefit. And so we have a website called Dashlink. You can type it into your favorite search engine and download the algorithms that we're talking about right now. Download all the papers about it. Ask questions. You can post a blog there if you want to. You can create a project and study it for yourself. This is one of the ways that we're trying to validate our results, so that people in the public can benefit from the work that we're doing.
We have that up on the screen now, but we don't have the URL with it, and I think it's dashlink.arc.nasa.gov.
Yeah, dashlink.arc.nasa.gov, although I type it into a search engine to get the to get the link myself. And what you can find there is applications of these things to other problems. So we've had people in the medical industry community, for instance, say, hey, you know, that problem that you're doing with the airlines, it sounds a lot like what we want to do with pacemakers. So can we use your algorithms? And I say, sure, go to Dashlink, download them, let us know if you use them and how it works out. So the scope here is enormous, and the problems are interesting, and the technology is fascinating.
All right, anyone else here down in front?
Yeah, question for both. If you look out 2 or 3 years, where do you think we'll be both on a technical basis and an operational basis in using these kinds of technologies?
I think it's hard to put a time frame on that. One of the limitations that we have in terms of doing more real-time interventions is the delivery of data. So for instance, we download our data every 5 to 7 days, and we plug it into the database via a memory card. And so by the time we have access to information off of the airplane, it's typically an event has come and gone. So we have to work on delivering that data either on a daily basis or even after every flight. And so and I think what our job is to sort of justify the safety benefit, because ultimately we know that when we make safety improvements, that's better for efficiency and customer service as well.
All right, and we have time for one more question. It has to be really quick. Go ahead.
Jeff, how did you become a pilot?
Thank you, Leela. That's a great question. I entered the Reserve Officer Training Corps in the Air Force back when I was in college at Oklahoma State University, and had an opportunity to go to pilot training after I graduated from college. So I did my initial flying and training in the Air Force, and then after I finished my career in the military on active duty, I joined Southwest Airlines and became an airline pilot.
All right, well, you're an inspiration to us all. All right, and that's going to have to be our last question. We've had a great discussion today, but we're out of time. On behalf of Associate Administrator Jaewon Shin at NASA, thanks to our guests, Jeff Hamlett of Southwest Airlines, Ashok Srivastava of NASA's Ames Research Center, and to our guests who joined us on video, Nikunj Oza, Bob Lawrence, Brian Matthews, and data mining experts Jaiwei Han and Stephen Boyd. You can learn more about NASA's data mining work by visiting www.nasa.gov. And I want to remind you that Ashok and Jeff will be our guests for a live web chat this afternoon at 2 Eastern Time. Bring your questions and go to nasa.gov. Click on the link for a chat in the NASA events ticker at the top of the page. Thank you.